This video we're going to talk about Le Chatelier's principle. Now Le Chatelier's principle is a really important concept, and it talks about systems that are equilibrium and then are put under a stress. So a stress is going to be something that might affect the equilibrium, and systems that are at equilibrium but then stressed, so taken out of equilibrium, will go back to equilibrium. So we're going to talk about how all of these different stresses might cause a change in the equilibrium position, then how the system gets back to equilibrium. We're going to see a lot of graphs in this section, and for any of the graphs, we're going to see that it's at equilibrium when all of the concentrations are the same, so it causes a horizontal line. So Le Chatelier's principle: if a stress or a change is put on a chemical system at equilibrium, the chemical reaction will shift to establish equilibrium again. Typically, this involves using something up or making something that was removed. So that kind of last little bit there is at the heart of a lot of this discussion. If you remove something, it's got to be replaced to get back to equilibrium, or if you add something, it needs to get used up. So the first situation or stress that we're going to look at is adding a chemical to a system at equilibrium. So by increasing the concentration of a chemical, and this is one of our stresses, and of course this still only applies to solutions or gases, things that have mole per liter, you increase the reaction rate that's going to use that chemical up. So here we've got this system here, and you can see that we've got hydrogen fluoride gas, this dichloro-difluoromethane, and then hydrogen chloride gas. The chemical that is in the reaction, but it's in the liquid state, does not show up in the equilibrium system because it's considered constant. So if you increased the concentration of hydrogen fluoride, so let's take a look at hydrogen fluoride in this reaction. Hydrogen fluoride is here. If we added that, then there are going to be more collisions in the reactants. The chemicals are going to bump into each other more frequently, and the more frequently they bump into each other, the more the reaction goes forward. And so it's going to use those collisions to drive more forward reaction. But as we do more forward reaction, we increase this, and eventually we're going to start getting more reverse reaction as well. But in total, it's mostly going to go forward reaction. So let's follow these chemicals. So here we've got our hydrogen fluoride is at equilibrium, right? And so is the hydrogen chloride and the dichloro-difluoromethane. Here we can see that we have had hydrogen fluoride added. So they've added the reactant, hydrogen fluoride, and when I say reactant, I mean left side of the reaction. And now it's going to get used up. So we're going to see that this chemical was added. There's a sudden increase in the concentration, and then it starts getting used up as the reaction goes forward. So it shifts the reaction forward, like we discussed, until it reaches equilibrium again and it flattens out. But while it's doing that, it's going to make the products. And you're going to see that the product concentration increases as they're being used up, or as it's being produced. So as this goes down to use it up to get to equilibrium, this goes up and this goes up. There's another thing that is a little hard to see in this graph, but the coefficients for hydrogen fluoride are 2, and for hydrogen chloride. So in this graph, the hydrogen fluoride should be used at the same rate hydrogen chloride is made, and that because the coefficient of this other chemical is 1, it's going to be made at a lower rate, right? Because as 2 molecules of this are used, 1 molecule of this is made. Whereas when 2 molecules of this are used, 2 of this are made. So anytime we add a chemical that is in the gaseous or aqueous state, as long as it's got a molar concentration, we need to use that chemical up that was added. And in a graph, it's going to look like a sudden change of one chemical that goes up. Now, it is possible to remove a chemical. So this is a harder thing to create. So it's possible to remove a chemical from a reaction. And often this is done by making it into a precipitate. So if you made something into a solid, then it no longer has a molar concentration. And a common way to do this is by adding silver ions, if there's chloride, and then you get silver chloride precipitate. So if you can make a precipitate, you're removing that chemical from the system. So in this question, or in this example that we've got here, it says if we add a chemical to the reaction, the chemical's concentration will go up, and the reaction responds to this by using up the new chemical to return to equilibrium. The reaction does the opposite to the stress. So if you add something, it will use it up. If we remove a chemical, the reaction responds by replacing it. So in this graph, you can see that these chemicals were at equilibrium, but then there was a sudden removal of hydrogen chloride. And as the hydrogen chloride is used up, as this is being removed, it shifts the reaction to replace the hydrogen chloride. So if we remove that, the idea is this. There are fewer possible reactions going this way, so relatively speaking, the forward reaction increases and we make more of the products. So as we remove something, we get less of that reaction going like that. So here, by removing the hydrogen chloride, it shifts the reaction towards the products, and it starts to make more hydrogen chloride here. And the other product also increases in concentration, and it uses up some of that reactant, right? And so in a graph, we can tell that something's been added because it's got a sudden change in concentration, or removed because it has a sudden decrease in concentration. And if I added a reactant, it shifts forward. If I added a product, so if I added some of this, it would shift this way to remove that chemical, right? It's going to use some of it up. By adding more hydrogen chloride, it would shift the reaction to go this way to use some of that extra stuff up. If instead I remove a chemical, then, so let's say I removed hydrogen chloride, it's going to shift this way to replace it because there are going to be more forward reactions than backward reactions because there are less collisions in the products. And it'll shift the reaction, it'll use some of this up, and these two things will increase in concentration. That's the essential concept behind Le Chatelier's principle. We're going to apply this concept to temperature in the next video.